Anderson here, and we'll have two other talks later this session by Christian LeBear and Matt Versaghi. Anytime you want to start, John, we are at 10:45. So,
is my screen up?
We can see your screen, the PowerPoint window. There's the presentation.
Okay. All right. So the major interest in this research is to understand how instruction and experience combine in learning. I'm going to be talking about video games, and just escape. I'm not happy with the way this is showing up on the screen. If I can do that, I can't. Oh. See, unable. There we go. We're familiar with the deep reinforcement learning efforts that are mastering a seemingly endless list of video games. What's probably less well known, but there have been a small counter tradition showing that humans can learn the same games without instruction, just like the deep reinforcement learners, in much less time, fewer games, etc. A few of these studies have also shown, not surprising, that if you provide subjects with instruction, they can learn even faster. But even if you give people instruction, they don't start out with high levels of performance. It requires considerable experience beyond that, just knowing what to do. And we developed an ACT-R model of video game play that starts with instruction and basically does the task. And I'm going to start with a little review of that model because it's relevant to the current context. So what I'm going to show you is two participants playing the game. One of them is a model and one of them is a human. You can take it as your task to decide human versus model, or you can just take it as an opportunity to see how this particular game works. The model learned the number of games, but we're going to look at the traditional Space Fortress game. And I'm going to show you participants on the first game and participants on the 40th game, the same pair. So it should be playing on your screen now. And what you should be seeing is a ship flying around. And the first game, the ability to navigate that ship is rather poor. A major challenge here is you're flying in a frictionless space and you have to learn how to combine various forces to actually achieve this particular circular motion. So we're seeing participants at a rather low level of performance here. So we can go on to the game 40. And you should see now a more fluid play by both participants. What they're doing is they're shooting at the fortress, trying to build up its vulnerability to 10. To do that, your shots have to be at least 250 milliseconds apart. Once the vulnerability is at least 10, you can hit a double shot less than 250 milliseconds and destroy the fortress. Now, if I had an audience that could raise their hands, I would ask which side was human and which side was model. The model was on the right side. Hopefully it sort of convinces you the model does behave sort of human-like. Typical audiences are making their choices at chance. So behind this model are sort of four features that are critical to its achieving human-like performance. One is that it's implemented in the ACT-R architecture, and that comes with realistic limitations on perceptual motor skills, and we don't have kind of superhuman response times that many of the deep reinforcement learners have. There's a long tradition of ACT-R instruction following models, and that's used here. Without the instructions up front, participants would learn much more slowly. But just with that knowledge, as I've said, you don't perform very well. One of the learning mechanisms is the ACT-R production compilation, which takes the initial declarative encoding of the instructions and with practice essentially converts direct action rules that just see the situation and act, allowing it to perform much more fluidly. But that's not enough because in these kinds of games, Successful performance requires learning the parameters that control successful actions, such as when to thrust, how to pace your fires, etc. And for that, we had to add a new module to ACT-R to learn these control parameters. And that was the topic of a paper that we published last year. Another variant of the Space Fortress, excuse me, I have actually going to show you some data next. So here's the overall performance in this particular task. You can see model and participants are matching up pretty well. It's the case that both show a wide variability in individual performance. The various models are quite different from one another just because of kind of their chances of running. The points that you gain is essentially get 100 points for every kill. So I'm showing in this slide the growth in number of kills over 20 games. Participants play 3-minute games. You lose 100 points for every death. And so we see the decrease in deaths. The model is a little bit outperforming subjects here. Besides these overall statistics, we matched a lot of detailed behavioral statistics about participants, like how often they actually miss the fortress when they shoot. So we see here model and participants matching up pretty well. So as I was going to say, we also fit the model to another task, which we call AutoTurn, which differs from the previous one only in that the ship is always aimed at the fortress. So you can't miss the fortress, and there's really only 2 keys that you have to use, a key to thrust and a key to shoot. We are interested in this game for purposes of the current talk because we created a variation of it that took away the shooter space fortress semantics. And this is what we see here. Essentially, you see a ball that's moving between 2 hexagons. The same 2 keys are relevant for shooting and for thrusting. And again, you're building up the vulnerability of the fortress, and you can take a double shot at a particular point in time. The reason for being interested in this is because we wanted to know how much of the learning without instructions is really a function of this space fortress shooter semantics. Okay, so, but here are the actual instructions that were given to people in this ball version. And what I want to emphasize about these instructions is they do not tell the participants what to do. They tell the participants how the game works. So for instance, it says, the ball naturally drifts clockwise and outward. Press the W key to move the ball inward. The longer you press the W key, the faster it will move inward. If the ball touches either hexagon, it will reappear at the start location. What you should do with that is kind of up to you, and subjects don't really have a lot of trouble acting on that kind of instruction. In the no instruction condition, this is what they were told. They were just told there are 2 keys, a W key, which is the key for thrusting, and the space key for shooting, and figure out how it works. So we basically have a 2x2 design here. There are subjects who have instruction, who don't, who have the space fortress semantics, do not. This is the overall performance of the subjects in those various groups. The big effect, obviously, is people learn a lot faster if they're told how the game works. It's of interest to consider those that reach a kind of a minimum level of mastery, which I'm going to define as having at least 300 points in the final game. That's something that even I can achieve. In the cases where there is instruction, most but not every participant reaches that level of performance. In the case where there is the space fortress semantics, but no instruction, 19 out of 30 reach that level. Where there is not that semantics, 11 out of 20 reach that level of performance. And it's of interest to look at only the successful subjects, the ones that master it, and that's what I have on the right graph. And the most striking thing to me about that graph is that the non-instructed subjects who get it in some sense seem to be moving towards the same asymptote as the instructed subjects. They haven't quite got there in 20 games, but they're clearly going there. Also of interest, there is this critical period where there's a large difference between those who have the space fortress semantics and those who do not. Okay, so one more thing I want to emphasize, and that is that the uninstructed subjects know what they're doing. So this is the subject who did best in the uninstructed group. She happened to be without the semantics. She said the ball will move on its own, but pressing W will change its direction slightly to the right of the current direction. Don't let the ball touch the lines or you'll lose 100 points. When the arena blinks, doing something will cause you to lose points. That's equivalent to getting shot by the fortress. She never quite figured that out. While moving the ball, tap the space bar somewhat quickly, but not too quickly, or it'll reset. Once it reaches 10 points, press it twice very quickly. That will get you 100 points. Pressing space bar consumes 2 points. She knows what she's doing. She's not sort of this deep reinforcement gel that sort of has somewhere in its connections knowledge of how to play the game. Here's a description from someone who reached mastery in the semantics version. And you can see the language with which they see the game is very different. Both of these subjects note that you have to get the vulnerability to 10. And think about that's kind of interesting because you can get the vulnerability to 12, 13, 14. The double shot still kills you, the fortress. It turns out 22 of the 30 subjects actually identify the 10 rule. And basically, they never shoot an excess shot, or almost never shoot an excess shot beyond the 10. There are 8 subjects who don't mention the rule, and they're averaging more than 6 shots before extra shots, wasted shots, before they kill the fortress. So people are basically behaving according to their knowledge of the game, their accessible knowledge of the game. So we built a model for this, and for initially I'm going to merge together the subjects who have the semantics and not, I'll break it out later. The instructed subjects are basically the same model. The instructed model is basically the same as we reported in our recent Psych Review article. The non-instructed models are new. And one thing I want you to note is that 56 of those models were not successful. Just like some subjects didn't figure it out, some of these models, the runs didn't figure it out. I have up above points that can be broken down into number of kills. The non-instructed models seem to be doing a little bit better than participants. And in deaths, they seem to be doing a little bit worse, but basically we're seeing the same trends in the population. Non-instructed models are identical to the instructed models, but they must first learn the causal contingencies, how the game works, which is what the instructions provide the participants with. The instructed model composes essentially a procedure from that causal knowledge. What I want to show you is how the uninstructed models build up a procedure for playing the game as they learn the causal contingencies in the game. So the model starts out just experimenting with the W and the spacebar key, but at some point in time, it's going to get to the place where perhaps they learn that spacebar will increment vulnerability, double spacebar will actually reset the vulnerability to 0, and not wanting that, they build up a little program, the models do anyways, which says, well, if I want to hit spacebar because I like my vulnerability to increase, but I got to wait for a time threshold between that, and while I'm waiting, I can experiment with the W key. Or they might actually learn what the W key does first, that it moves you inward, and that hitting the border causes death, and then they'll build up a little program. I don't want to get too close to the outer border. If I do, I'm going to hit W. Otherwise, I'll experiment with the space bar. Eventually, they're going to learn the other things, and they come up with this little procedure, which is if I'm not too close to the outer border, then just basically hit the space bar. Much later, typically, they learn that hitting the space bar twice quickly has another effect. It actually increases the points you get, but the vulnerability has to be high at that point in time. At which point in time, the models build up this sort of more or less complete program, check whether the vulnerabilities are below threshold, do one thing. If it's above threshold, do something else. what that threshold is, the models don't initially know. They're actually using the control tracker in the ACT-R, the new component, to kind of hone in on where that is. But at some point in time, most models wind up identifying that the vulnerability of 10, and then they put in a hard threshold for which way they want to go, the hard threshold of being the vulnerability being 10. So now what I want to do is kind of identify how these particular contingencies are identified. So I'm showing you a potential state that could be available to a model. It was a model that caught halfway through the game, and these were the experiences it could have attended to. There are various potential causes like hitting the border, hitting the space bar, various possible effects like dying, your vulnerability going to 0. And actually, I'm going to focus on the case of the vulnerability getting reset to 0. And we can kind of summarize all of these particular experiences in a 2x2 table. And so looking at a competition between actually the correct hypothesis on the left, that double space bar is what sets the vulnerability to 0, versus on the right, just that space bar sets the vulnerability to 0. And focusing on the left here, we have a little 2x2 matrix. There are 4 cases where they hit the double space bar and vulnerability went to 0. But actually twice they hit the double space bar, and once they were distracted by a big gain, and the model was, and didn't notice the vulnerability going to 0. And once the model thought it hit 2 space bars in rapid succession, but they're far enough apart so that it actually got a vulnerability increase. And then there are 2 cases where it thought it hit a double space bar and didn't see the vulnerability go to 0. Well, in one case, it had hit the double space bar, and then it had followed that by a W key, which is closer to the vulnerability getting reset to 0, and so that was attributed to the W key. The other case, it thought the 2 keys were close enough together to be a double key bar, but they weren't. And so, it thought the keys were far enough apart not to be a double space bar, but they were close enough to produce the reset to 0. This is what would happen if the model detected and stored everything that happened. That's sort of unrealistic. The most powerful models we run detect about 50% of their potential experiences. We run models where they just detect about 10% of their experiences. And the question is, how is the model going to use these experiences it's recording to make an inference about when a potential cause produces an effect? This is kind of the information that's available to it, the cases that it's stored away in memory of potential causes and effects. And what ACT-R does is it attributes a causal relationship when a pairing becomes so reliable that just seeing the cause is enough to have the effect retrieved, and then the effect is actually confirmed in experience. And it turns out in ACT-R that's going to be controlled by the strengths of associations from the cause to the effect. The ACT-R learning equation for associations has not been used very much, but this was the original form of it, which essentially said the strength of association should be basically the log likelihood ratio. The probability that the cause is present if there is an effect is seen, and probability the cause is present if the effect is not seen. In terms of the 4 frequencies, it breaks out as into these log quantities. It turns out there have actually been a lot of experiments over the decades presenting participants with sequences of potential causes and effects of their absence, and then asking participants whether there was a causal relationship between a potential cause and effect. Our model, like one of the successful models for this literature, Patricia Chang's Power C, predicts that subjects are actually largely insensitive to sample size, just the relative sizes of the A, B, C, and D frequency. And they weigh the cases where the cause is present more than they weigh the cases where the cause is absent. So we sort of have a kind of a reasonable model of this kind of causal attribution. This shows the attributions that were made by the model across the 20 games, actually 400 models across the 20 games. And what we're looking at is the probability that a particular attribution was made at a different point in time. Some things like what the spacebar typically does, which is increase the vulnerability, or the W key change in the direction of the ship. Those are inferred pretty quickly by almost all the models. Other thing, and like the fact that there's this 10 threshold for vulnerability, is identified much later, and actually only about 2/3 of the models actually ever identified that. So what we've done is try to pursue the hypothesis that basically the difference between the semantics and no semantics condition is related to the probability of detecting a particular relationship. So we have this low condition where only between 0 and 20% of the possible pairings are actually stored away, and the high case where 15 to 35% of the pairings are detected and stored away in memory. And what you can see is it does a pretty good job of matching up with the difference between semantics and no semantics. Some of these models actually fail to achieve 300 points, and that is when you look at the models because they fail to make critical causal inferences. Only 1% of the high models fail to reach 300 points, while about 1/3 of the low models do. We can break this down in terms of what's sitting behind points. We look at the kills. Again, it seems like the high and low detection does capture the difference between semantics and no semantics, including the period of time where there is this large difference. If we look at deaths, interestingly, the participants in the two conditions don't vary, and they tend to behave like the high model. And so it seems to indicate that deaths and their effects are kind of equally obvious in both conditions. So the difference is somehow that you make more kills in the semantics condition. And basically that's using your shots efficiently. The two ways you can waste shots, one of them is you can hit that double space bar before you reach the threshold of 10 and you get a reset. So I'm looking at the frequency of resets. Interesting that two levels of the model don't really differ very much in their resets. The participants only show a difference early on, and that is the subjects of the semantics conditions are so thrilled by seeing their ship, missile go out of the ship when they hit the space bar that they initially hit the space bar madly before they understand anything and get lots of resets. So that's not where the difference between the semantics and no semantics lies. The other way you can waste shots is you can go past that threshold of 10 and waste extra shots before you execute the double shot to kill the fortress. And we can see that's where the difference does lie between semantics and no semantics, and it's a difference captured by the high and low detection models. And I think this is the critical contribution of shooter semantics in this game, which is that it makes salient the concept of a vulnerability threshold. Okay, so I'm going to conclude. The big story is that operators for playing a game are learned from an understanding of the causal structure of the game. That causal structure can either be instructed or it can be inferred. Now, in principle, just having a knowledge of how the game works and actually coming up with a plan for playing the game could be a real challenge, not for these particular games anyways. But mastery requires more than just knowing what you should do. That's what the published ACT-R model was about. And when you don't have instructions, at least the ACT-R model learns the causal links by identifying reliable contingencies in the game, which it seems like we can do fairly well by just using the strength equation for associative strengths. We've seen that success in the model is detected by kind of the relative salience, how many of the possible pairings you detect, and that seems to be related to the contribution of semantics. I think there's an interesting connection here to work that I've done previously with Hee-Seung Lee, looking at learning of mathematics. Mathematics skills and a lot of similar skills are actually learned very frequently from examples rather than instructions. And what's critical is to identify, what's critical to success is to identify the critical relations in the example. And our research had shown that this can be much facilitated by highlighting, often just with this sort of choice of color, the critical relationships. And that's it. Thank you.
All right, thank you, John. And we have a few questions from the audience. One question from John Laird: are there any differences in the subject's experience with the computer games, the human subjects?
So almost all of, well, actually every subject we have in this experiment has played computer games in the past. I think we've only once ever gotten a subject who hasn't. They vary in how much they played games. And there is a marginally significant relationship in the no instruction condition between the number of hours you report playing video games and your success in the no instruction condition.
Oh, thank you. And Manuel asks, is the ACT-R model available?
The ACT-R model that was associated with the psych review paper is out there, basically attached to the paper. I'm more than happy to send copies of the model. Maybe I'd want to write up some instructions about how to run it for the no instruction condition.
And another question, could you discuss more the factors that cause individual differences among the non-instructed models?
Well, there's only one thing that really, well, partly it's a luck of the draw. You happen to fail to notice a critical relationship over and over again. Sometimes incorrect causal attributions are made, but it's pretty rare. The factor that is being, in some sense, is being controlled is just the total, just the probability that a particular, and we haven't had sort of the model be more attentive to certain relations than others, but basically the probability that any potential relationship gets attended to and stored. And the models that aren't so the models that are pre-programmed to ignore a lot of those contingencies tend to do poorly. The models that are allowed to detect a large number of those contingencies do universally, at least, or at least almost universally, get the criterion of 300 points. And there's also, within those models, a fairly strong relationship between that detection rate and the number of points people achieve by the end of the game.
Thank you. And Neil asks, which I think you might have answered a bit in the talk right after he asked this, but how does the model know what the causes and effects are? You talked about the log likelihood.
Yeah, so I mean, there are two parts to the answer. First of all, there are a set of potential causes and effects it attends to, and it's just gifted with that knowledge that these are potential causes and effects. Many of the pairings are sort of irrelevant, and actually some of the causes are irrelevant to anything happening in the game too. But it sort of has a hypothesis space of things that it will attend to. As you said, the strength of this, well, so there are two pieces to that. Basically, it's what it attends to, it stores. And if it stores enough instances of a particular cause-effect combination, the associative strength will increase to the point where it can be retrieved.
And Stephen asks, how do you compare your notion of causal attribution to notions of causal relations as being things like counterfactual statements? For example, if A had not occurred, then C would not have occurred, as a way to state that A causes C.
Yeah, so I think we're dealing with particularly simple causal situations here. And are these situations where the inference from cause to what you should do is fairly straightforward. One can certainly imagine, it must be true of a lot of games, that there actually is required a lot of reasoning to go from one's understanding of what the causal structure is to the appropriate inferences about what one should do, and certainly counterfactual reasoning would be part of that.
All right, thank you. One more question, but maybe Christian can start setting up his next talk. While we
release my screen here yet?
Yeah, we still see your screen, John.
Okay, so
Frank.
I need to. I can do a new share. Is that I can? Does that stop it? No, I'm sharing. How do I unstop my sharing? Stop.